Hi, welcome to Lesson 8 of Module 5, Graphs of Simple Nonlinear Functions. So today we're going to look at some nonlinear functions, and we're going to see that unlike linear functions, which have a constant rate of change, in other words, the slope never changes along a line, with nonlinear functions, that's not true, and the rate of change will change at different points on the graph. Okay, and so we'll be able to determine whether an equation will graph as a linear function or a nonlinear function by looking at the rate of change. And we're also going to use what we have learned about linear and nonlinear equations to give us clues to whether a particular function will graph as a linear or nonlinear. Okay, so let's get started. And some of this may be review for some of you, so feel free to skip through the examples as you look at the classwork if you know you feel confident about what's going on. Okay, so let's look at exercise 1. A function has a rule so that each input x is assigned an output of x squared. Do you think the function is linear or nonlinear? And explain. Okay, so you can think whatever you want, but if you you might want to pause it and think about it. But if you remember when we talked about expressions, linear and nonlinear expressions, we said that linear expressions were ones where the exponent on the variable was 1 or 0. And this has an exponent of 2. So you could say something to the effect of, because of the exponent of 2 on the output, I think this will be nonlinear. Okay, so let's actually do it. Let's look at it, and this will give us a little bit more room. So I've labeled input x and y. Remember, it's input and output. Input along the horizontal axis, output along the vertical axis. And we have some inputs that we're asked to find outputs for. So if my input's -5, my output, which is x squared, would be 25. Whoa, doesn't want to write. Okay, and so on. -4 times -4 is 16. 3 squared is 9. 2 squared is 4. 1, 0. And then we get some repeats here. So remember, this can still be a function, even though some of the outputs will be the same for different inputs. But each input has a unique output. I'm not going to get something different for -5 the next time I put it in this function. The output for -5 is always going to be 25. It just so happens that the output for 5 is also 25. So let's see what that looks like on our graph. So I'll get some points here. We have the point 0, 0. And then we have the point 1, 1, and also -1, 1. We've got 2, oh, wait a minute. Let's look at the scale. We've got a different scale on our y-axis from our x-axis. So here we go. There's 1. 1 and -1 and 1. Okay, so for -2, we've got 4, which is right here. +2 is also 4. -3 is 9. +3 is also 9. And got -4 at 16. +4 at 16. So I've just made an input-output table, and now I'm graphing the points. So negative 5 is 25, and positive 5 is also 25. Okay, so that's our graph, and so we could ask ourselves, what shape does this graph appear to be taking? Sometimes people view this as two lines, you know, like try to draw a straight line here or make this like a V shape, but it really is a curve. It really comes right through here and curves right back up. And we can almost see visually, not almost, we can see, let me get a different color. If I look at the rate of change between these points, I can see that it's changing. Okay, it's getting steeper or less steep? Yeah, it's getting steeper and steeper as x increases, or as negative x increases this way, the absolute value. So this graph gets steeper and steeper and steeper, and that's what makes it not a line, because the rate of change is different. So let's actually calculate those rates of change. And so we're going to use the data from this table, but I'm going to have to go to a different screen. But we're going to use, part E says find the rate of change using rows 1 and 2. So that would be right here. So we're going to use those 2 points, and then from 2 and 3. So we're going to find this rate of change, and then we'll pick 2 other rows. All right, so let's get a blank page to do that. Okay, so this graph does appear to be taking the shape of a curve. And we're going to look at the rates of change now. So E says to find the rate of change using rows 1 and 2 on the table. So row 1 would be the ordered pair negative 5, 25. And row 2 would be negative 4, 16. So the rate of change for this would be the difference in the y's, 25 minus 16, divided by the difference in the x's, or the horizontal distance. So this would be negative 5 minus a negative 4. And so 25 minus 16 is 9. Negative 5 minus a negative 4, it's the same thing as adding the opposite, right? Subtracting a negative. So this becomes negative 1. So the rate of change here is negative 9. So where do we see that on the graph? Let's go look at it. So on the graph, we have this slope triangle right here. This is, this is 9, and this is 1 here. So that slope between those 2 points on that curve is negative 9. Okay, so find the rate of change using rows 2 and 3. So rows 2 and 3 are negative 4, 16, and negative 3, 9. And so our rate of change would be the difference in the y values divided by the difference in x. This would be negative 4 minus a negative 3. 16 minus 9 gives us 7. No, sorry. 16 minus 9. Okay. So simple arithmetic can sometimes be hard. Okay, so the rate of change for between those 2 points is negative 7. So we went from negative 9 to negative 7. So I already know we don't have a constant rate of change. So now I'm asked to find the rate of change using any 2 other rows from the above table. So we're going to pause the video you can do that, and I will do it as well. Okay, so I chose two different sets of points. I chose 2, 4, and 4, 16, and I found that the slope was 6. And then I chose 0, 0, and 1, 1, and I found that the slope was 1. So I've got 4 different rates of change, 1, 6, -7, -9, and my guess is that I would have even more different rates of change if I checked more pairs of points. Okay, so H says, return to your initial claim about the function. Is it linear or nonlinear? Justify your answer with as many pieces of evidence as possible. So this appears to be this. Okay, let's start talking about our evidence here. The graph looks like a curve. Okay. It looks curved, not straight. That would be one piece of evidence. The rate of change is not constant. Therefore, the expression x squared is not linear. Let's go back and look at it one more time. Here's our function, and if I can try to draw a smooth curve through here, and that would be it. So it's a continuous function. This is called a parabola, but it's a U-shaped curve. Okay, let's look at another example. Okay, so a function has a rule so that each input of x is assigned to an output of x cubed. Do you think this function is linear or nonlinear? Explain. Okay, so you might pause and write down your thoughts on that. Okay, so maybe you said this is non-linear. Whoops. Because, this is the explaining part, because the exponent on the variable is a 3. Or we could say the exponent on the variable is greater than 1. Okay, so we can think, what do we expect this function x cubed to look like? Okay, the variable is greater than 1. All right, so let's work on this one. So we've got some inputs and outputs. For one like this, I would say it's okay to use a calculator to do the to find the outputs for this function. So why don't you go ahead and pause it, and you can work on finding those outputs using a calculator. Fill in the table. Be careful with negative and positive signs on this. Okay, so you can check your results against these, and now we're going to plot them. So we've generated some inputs and outputs. So this is a little different than the x squared, notice, because of what happens to the negative inputs. We had all these negative inputs. The output is also negative. If the input's positive, the output's positive. With the x squared, all of the outputs were positive, right? Nothing could come out negative when we multiplied it by itself. Okay, so let's we're just going to roughly plot some of these points. We can't be super accurate, but we can start with we start with 0, 0. 0 cubed is 0. And then let's do 2. We'll do positive 2 gives us 8. Negative 2 gives us negative 8. Okay, so we had positive 2 cubed is 8. Negative 2 cubed is negative 8. I like to start with the easy points to plot. So the other easy point to plot are -1, -1, and 1, 1. So let's do that. 1, 1 goes right there. -1, -1 goes right there. Okay, and now we had this positive 1/2 is 0.125, so that's really close to the axis there. So we can kind of get a pretty good idea what's going on around the origin there. So let's move to 1.5. So we'll do this one. Positive 1.5, 3.375. So just under 4. And negative 1.5 would go right in there. And then we just have one left to plot. And that's 2.5, which is 15, a little over 15. So 15.5, so right in there somewhere. And negative 2.5 is also just over 15. Okay, so do you see the shape that this these points are starting to take? You notice it kind of curves in, flattens out through here, and then starts to curve pretty steep again. So that's the basic shape of this. Let me pick a different color to draw the line so we can still see the points. So it comes right through there, pretty much. That's not great, but close. Okay, so it does appear to be taking the shape of a curve, though. We've got a curve here. All right, so we are asked again to find the rate of change using some different points. And here is the right page that matches yours. Okay, so find the rate of change using rows 2 and 3. So what are the points in rows 2 and 3? Looks like we've got, in row 2 is -2, -8. And in row 3 is -1.5 and -3.375. All right, so we're going to find the rate of change by looking at the difference in the y coordinates. I got -8. I'll move over here. -8 minus a -3.375. And that is over -2 minus -1.5. Okay, so in both of these we're subtracting a negative, so we're adding the opposite. So in the denominator, it looks like I've got a -0.5, -5/10. And in the numerator, I've got a negative, we're subtracting really, so at -4 and 625 thousandths. So if I, hopefully you're using a calculator on this, that's fine. This slope is 9.25. It's a pretty big slope. 9.25. Okay, so the rate of change between rows 3 and 4. So I've got row 3 is negative 1.5 and negative 3.375. And row 4 then would be negative 1, negative 1. So my calculation here is going to be negative 3.375 minus, that's the difference in the y coordinates, so minus a negative 1. And that is over negative, what do we have? The difference in the x coordinates starting with the first point. Negative 1.5 minus a negative 1. So once again, we're adding 1 in both of these cases. So this is negative 2.375 divided by negative 0.5 again. Negative 5/10. So this slope here is smaller, 4.75. So there's two different slope values already, which is a major clue that it is not a linear function. So let's look at rows 8 and 9. 8 and 9 are these points. All right, so there's the points, and so the rate of change is the change in y. And I like to do this so that the math comes out the easiest. It doesn't matter which direction I go as long as I'm consistent. So the difference in the y's is 3.375 minus 1. So there's a y value and a y value. And then that is divided by the y value that goes with this output. So I've got the x value, I should say, 1.5 minus 1. So this is over 1.5 minus 1, which is the difference in the x coordinates. So I've got, looks like that same slope again, 2.375 divided by 5/10, and that result came out to be 4.75. Write it this way, 4.75. Okay, so we had different rates of change depending on which points we choose. So we know for linear equations that that's not the case. No matter what points we choose on that line, the rate of change is always the same. So we have a lot of evidence that this is not a linear function. So in H, it asks you to return to your initial claim about the function. Is it linear or nonlinear? It's nonlinear. And justify your answer with as many pieces of evidence as possible. So what are the types of evidence that we have? We have the graph itself, its shape. We can tell it's not linear just by looking at it after we plotted it. So we have the shape of the graph. We have the rate of change. Data is not constant. And what else do we have? We have the equation itself, y equals x cubed. So we could notice some things about the equation itself that's different from the linear ones that we've been graphing. And we talked about linear expressions in Module 4, having to do with the exponent on the x. Okay, so got one more example here that we're going to graph. And this is, the output is 1 over x. Do you think this function is linear or nonlinear? So you could talk about that and then figure out the outputs for these given inputs of 1/10, 2/10, 4/10, and then we're going to plot those. So work on as much of this as you feel comfortable, and then I can work through it together with you. Okay, so let's start looking at some of these inputs and outputs. So if x is 1/10, then 1 over x would be 10, because 1 over x is the reciprocal of x, okay? 2/10 would be 10 over 2, which would be 5. 4/10 would be 2.5. 1/2, the reciprocal of 0.5, which is 1/2, would be 2. The reciprocal of 8/10 would be 1.25. Reciprocal of 1's the easiest one there. That's just 1. I'm just going to fill in the rest of these. You could have used your calculator or what you know about fractions, preferably, to get these. Reciprocal of 2 is 1/2. And some of these we have doubles on our table. We have the reciprocals of each other, such as 2.5 and 0.4. The reciprocal of 5 would be 2/10. 0.2. All right, so we can start plotting some of these values. And my tool for plotting isn't very accurate, but I'll try to do the best I can. So there's 1, 1. So I'm going to start at the top. So 1/10 and 10 right there. And 2/10 and 5. So we just barely come over a tiny bit, and we come all the way down to 5. 4/10 and 2.5. It's a little less than a half in there. So we're seeing different slopes already. 0.5, so 1/2 and 2. So we're right in there. And 8/10 and 1.25. So right in there somewhere. 1.6 and 0.625. A bit higher. 2 and 1/2. And then these are just getting closer and closer to the x-axis. So you can see what's happening here is it's approaching the x-axis as we come down through this way, and it's approaching the y-axis as we go up here. So x can't be 0 because 1 divided by 0 is undefined. And so then y can't be 0 either. So there's our function. So it's clearly nonlinear. So 1 over x we know is going to give us a nonlinear function. So now we're going to look at the rate of change between these points. And so I'm just going to quickly go through this. I've copied down the ordered pairs for the ones, rows 1 and 2, 2 and 3, and then I chose 2 points down here. So the rate of change is the difference in the y divided by the difference in the x. Okay, this is going to be a negative slope because it's going to be 5 over negative 1/10. So this is a slope of negative 50, actually. It's a pretty steep slope. So what part of the graph is that we were doing? Well, it's this part right up here. Between this point and that point, the slope is -50. So now we're going to check the slope between these 2 points, these next 2 points. And we're going to find it's quite a bit less. So we've got 5 minus 2.5, that's the change in y, over 4/10, over 2/10 minus 4/10. So we've got 2.5, did that subtraction, over -2/10. So this is -12.5. So still a steep slope, but quite a bit less. And so we already know this is nonlinear, right? So let's do one more. We've got 1 minus 0.5 over 1 minus 2. So this is 1/2 over -1. So that's negative 0.5. Okay, so once again, return to your initial claim about the function. Is it linear or nonlinear? Justify your answer with as many pieces of evidence as possible. So we're going to cite the same types of evidence as in the other example. There's the rate of change is not constant. The shape of the graph is not a line. And the equation y equals 1 over x tells us something as well. Okay, so go ahead and write that out and then continue along. Okay, so the rates of change in those 3 examples were not constant, okay? And so we know for linear equations that the rate of change is constant. And that kind of defines a linear equation. Rate of change is a constant. So no matter what 2 points we pick on that function, the rate of change will always be the same. For nonlinear, the rate of change is not constant. Okay, it changes. And we saw that in all 3 of those examples. Okay, and the other thing that we may have noticed is something about the exponent of x, and something that we saw in Module 4, but let's write these 3 equations. We had y equals x squared, we had y equals x cubed, and we had y equals 1 over x. So we had an exponent of 2 and of 3, and this exponent is actually -1 here. So whereas with our linear equations, we could always write them as y equals mx plus b. So the exponent on this term, the exponent equals 1. Right there. So the exponent is 1 on the x variable in a linear equation, and it's not 1 in a nonlinear equation. So that's another clue that can help us identify these. And so in these next several exercises, we're going to look at some rules that describe a function. If you want to, you could use a table of inputs and outputs and plot the functions on the coordinate plane to answer questions, but you might not need to do that. So let's look at the first one. You can do these independently, so if you want to pause now and just walk through them yourself, that would be good, and then you could come back and check your answers on the video. All right, so for this first one, the function is y equals x. So if you think that's a pretty simple xy table, right? Because whatever I put in for x, I get out for y. Nothing changes. And a quick sketch of that graph would just be, whoops, not that line. I would have to go right through the origin. It would be that line, and that's where all the x's and y's are equal. So hopefully you guessed that that one was linear. That's a linear equation. It's actually a form of y equals mx plus b, right? Where it's y equals 1 times x plus 0. Okay, so y equals x, linear function. Okay, let's look at the next one. 5, we've got the equation y equals 2x squared minus x. So, that one's going to be nonlinear because of the exponent on this term right here, the 2x squared term. And this is actually going to plot something like that. It's very much like the y equals x squared, just shifted over a little. So that's a linear, a nonlinear equation because the exponent on the x term is not 1. This one has an exponent of 1, but this is going to change the whole thing. Okay, what about this next one? 3x plus 7y is equal to 8. Is that linear or nonlinear? Well, what is the exponent on the x is a 1. Another thing you might notice is that this is standard form of a linear equation. Remember, ax plus by is equal to c. That's a linear equation, and it could be put in another form, but we don't need to worry about that. Okay, so that's going to graph as a line. What about this next one? Y equals 4x cubed. So y equals 4x cubed would be nonlinear because this one's linear, nonlinear, because of the exponent on the x variable. X to the third power is going to make that nonlinear. And the shape that this one's going to take is that kind of coming through and going down like that, which is kind of cool. Okay, so that's a nonlinear function. Another one here, 3 over x. I'm going to write it bigger. 3 divided by x equals y. Okay, is that linear or nonlinear? Okay, this one might be a little harder to see because there's not an actual exponent on that, but that's a nonlinear function because 1 over x is the same as x to the negative 1. So what that means is that that x doesn't have an exponent of 1, it has an exponent of negative 1. So that's going to make it nonlinear. This one, how does this one graph? This one is something like this, which is kind of cool. Okay, so let's do the next one. 4 over x squared is equal to y. Okay, well that one definitely nonlinear, right? Due to the exponent, and that's actually a -2 exponent on the x variable. Okay, so it's going to lead to a nonlinear equation. This one looks something like this, has 2 parts, and graphs like that. Okay, so there's lots of graphs. You'll get in much more depth with these nonlinear types of equations in high school. Okay, so what shape do you expect the graph of the equation x squared plus y squared equals 36 to take? Is it linear or nonlinear? Is it a function? explain. Okay, so probably nonlinear, right? Because of the exponent on the x term. But is it a function? So to answer that, we might need to do an xy table. And I would start with easy numbers. Put in 0 for x. If I put in 0 for x, then I have 0 plus y squared is equal to 36. So y could be 6. But y could also be something else. Y could be -6. So that gives us two things that y could be for the same input. So this is not a function. I'm going to write that over here though. This is not a function because of that. And it is nonlinear because of the exponent. And it's a really fun one to show you too. So what this equation is it's a circle around the origin and the radius is 6. So this is the point where x equals 0 and y equals 6. So this is the point 0, 6, and this is the point 0, -6. And then, of course, I've got 6 at 0 and -6, 0. Okay, so that x squared plus y squared equals 36 is actually the graph of a circle. But it's not a function, and it is nonlinear. All right, so what have we talked about today? So we have looked at some nonlinear functions. We've looked at the rate of change and saw that for these nonlinear functions, they do not have a constant rate of change. And we could also look directly at the equation. We could examine the equation and note the exponent on the variable x. If it's equal to 1, then we're going to have a linear equation. If it's not equal to 1, then the equation would be nonlinear. Okay, so you have your problem set. You'll be graphing some of these, and others you'll just be answering questions about. Okay, good luck with that, and we'll see you back here for lesson 9. We're about to wrap up this module.